So, why does sodium explode in water? Or, let's rephrase it. Let's have a bit of fun with alkali metals. So I'll ask some questions. So, what do you get when you toss water on someone holding sodium? An explosion, right? But why? Why do we get this explosion? So, let's make a quick poll. I mean, who has done it? Who has thrown? Okay, good. So, it's like, I think the limit is like, age limit is 30, 40, right? So I don't know when the US-wide ban on throwing sodium into water in high school came. It's still legal in Europe. So if you want to, you do your high school studies in Europe, you can still do it. So, well, we'll ban it soon. But actually, one of my missions here is actually to convince the authorities, I don't know if anybody responsible is here, that it actually can be done in a pretty safe way if you know what you're doing. And then, yeah, maybe this way we'll get it back. So be my, I'll spread the gospel, be my evangelists about safe throwing sodium into water. But if we want to do it safe, we need to first understand what's going on, right? And you would think everybody understands that. This is like the classic textbook thing that you learn in elementary school, and I heard there in some advanced kindergartens, they're already explaining you how this is happening, right? So let's go briefly through the textbook explanation. So you take a piece of alkali metals, and alkali metals are this first row column. This is my English. Column, right? First column. And so they have this one extra electron that they held very loosely to. So if you actually put them into water, they very easily let this electron go into water. That distinguishes it from like precious metal, like my wedding ring, right? If I throw my wedding ring into water, which I will not do, I may lose it, but the gold will not lose its electrons. It will stick to it. That's why this wedding ring will not explode in water. But another metal, sodium, would explode in water, right? And the classic explanation is these electrons go into water, and they are very reactive. They find water molecules, they react, they create hydroxide. That's the thing you clean clogged toilets with, by the way. And, but that does not explode. And hydrogen gas. And hydrogen does ignite and can explode. Think about the Hindenburg. Who was alive in 1937? Yeah, I believe you. Okay. You were, yeah, our distinguished founder was alive, yeah. And that happened in New York, right? Somewhere. Yeah, anyway. It's New Jersey, yes. Close. I'm getting old and sidetracked. Okay, let's focus. So there's hydrogen, and that can ignite. And another thing is, there's a lot of heat being created because the process is exergic. I mean, it creates heat. By the way, like 1 kilo of sodium creates more energy than 1 kilo of TNT when it properly explodes. So that's about what we're talking about. Safe stuff, right? Yeah, okay, cool. So it all makes sense, right? I mean, the electrons come to water, they react, create heat, create gas, create hydrogen, hydrogen ignites, and boom, right? And that's it. I mean, that's what the teacher will tell you. Well, there are a few problems, right? First thing is, I mean, hydrogen can only ignite if you have oxygen, right? So you can do the whole experiment without oxygen. You just put argon there or nitrogen. It still explodes. Not as beautifully, but it still explodes. So that's one problem with the explanation. But there's another problem. And that is, I mean, we're in the Wild West, right? So, I mean, this is the land of explosives here. I mean, all the mining and shooting. If you want to shoot a gun, you need to have some explosive. So you're using gunpowder. And what is gunpowder? These are chemicals that are finely ground. And this is pretty much the necessary condition for explosion is a well mixing of reactants. You have to put the stuff that reacts in a very fine grinded manner so that there is a lot of contact. So when the reaction starts, a new reaction can start and new. And this is this kind of exponential runaway that leads to the explosion. It's not just a chemical reaction. Not every chemical reaction is an explosion. You need this runaway situation. And you ensure it by mixing of the stuff. Here, it's anything but. I mean, you chip a piece of sodium, macroscopic piece of metal, and you throw it into water, macroscopic water, and the reaction can only run at the point of contact. It's even worse. You're creating this hydrogen gas, you're creating vapor because you're heating it, so you're separating the reactants. If you separate reactants physically, there cannot be a reaction, right? So it should actually be self-quenching. There should be no reaction. It should just quench. It should just not work, right? So we have a problem. All right, so we need a controlled study. And remember what the teacher did, right? So the teacher pulled out out of petroleum this piece of this really ugly oxidized sodium, chopped it with a knife, threw it in water. If you were lucky, it exploded. If you're not lucky, it was kind of fizzing around. And then when the students leaned over, then it exploded. That probably led to this US-wide ban, right? It's very erratic, right? So we need to do it better, scientifically. So this is the old days in our group when I hired this guy. His name is Phil Mason. He's really behind all this. I'm just the voice. He was a postdoc at Cornell and getting positively bored. He traveled every summer to the Wild West with a lot of sodium and potassium in his car, in the trunk of his car. And he would go to some remote place and set up this experiment. And he would throw like 10 grams of sodium into water, leaned back quite a bit. He once told me that the key to a long life is not to shorten it. And and then he would shoot a video and put it on YouTube. By the way, if you type Thunderfoot, you can see these beautiful videos. So this is cool, right? You get nice videos, but do we get any understanding from this? No, totally zero. This is like in the high school, no understanding. I mean, it's cool, but no understanding. All right, so when he came to Prague, we set up a much more sophisticated experimental setup. I mean, Judy introduced me as a computational chemist, and that's actually right. And computational chemists don't have labs. But we had a balcony. So we set it up on a balcony, and this is the setup we had. And it's pretty sophisticated. We have this Nerf gun that was remotely controlled, and on the tip of the projectile, we put a piece of sodium, and in a controlled way, stepping back about this distance, we threw it into water, and we had this really expensive $200 camera, and we shot it about 500 frames per second. And that was actually enough to get some first idea, what is this missing thing that actually allows for the explosion. But, you know, science moves forward, right? I mean, this is not good enough, particularly if you have this broken polystyrene. So then we started to talk to real experimentalists, and I was running around our institute, and I was saying, hey, would you help us do this simple experiment? I said, sure, people are nice in Prague. And then they said, what would it be? I said, it's just a small explosion. And they said, well, how about not? And I had to go all the way to Germany to find this brave guy. His name is Igor Bauerecker. He actually was in Telluride a few times, and it's in Braunschweig, North Germany. And he said, yeah, I have this lab, you know, this is underground lab, and we do messy stuff there. So yeah, why don't you come? And that actually put it to a totally different level, like which I would call scientific. And there were there were like 3 tricks that we did. So one thing was we didn't chip off a piece of sodium. I mean, those of you who've seen sodium, just sit down here. No, it's kind of it's a metal, right? It's a soft metal, it's a solid. By the way, potassium explodes also very nicely. It's even more dangerous because it oxidizes, it can explode even without water, but it's also a solid. But the cute thing is, and I don't know if anyone of you who is a chemist here has done it, if you actually press a piece of sodium against a piece of potassium, the thing liquefies. You get a liquid alloy. This is a well-known thing that if you mix 2 atomic metals, the alloy actually has a lower point of melting, so you get a liquid at room temperature. This is really cool. You can put it into a syringe, you can clean it very nicely. So we always work with this sodium-potassium alloy, which is liquid, so we're always kind of squirting a drop of this, and the trick is, I mean, small amounts, because when it explodes, and it explodes in the wrong time, in the wrong place, I mean, you get few scratches, but you survive. But face shields are, actually, by the way, face shields are good stuff, as you see here. So that was one trick, to use the sodium-potassium alloy. The other trick is we had this 1 meter long tube that we filled with argon, and that ensured that there was no oxygen, so when the droplet was falling, it didn't oxidize. It was pure metal. So there was a very good contact with water, and then it exploded on contact. And the third thing, we kind of upgraded from this $200 camera to this camera. This is a high-speed camera that can do as much as 30,000 frames per second, every 30 microseconds. This process is fast. Now, this is $200, this is $50,000. But you can rent it for a weekend for $1,000. And they ask you what you're going to do with it, and you just say, I'm going to shoot some movies, which was absolutely true. Yeah, so that's the trick. And then we just focus the camera. Either we focus it from above, and the nice thing is, with this setup, it exploded exactly at the point of contact, because you cannot move this camera when you're making 10,000 frames per second. So you either look from above or from below. So let's see what we got. So I'll show you a few movies now. So you see this is the speed, 11,000 frames per second about. So it's really, really fast. If I would just do it in real time, it will be over and you wouldn't see anything. So I'm going to slow it down a lot, and I will everything play twice. And I will even slow it down when it starts exploding. And I will also, okay, this is like, I'm introducing a very short movie by a very long speech, so it's probably wrong. But anyway, I will also compare it. I will throw this piece of sodium-potassium alloy, and then I will throw just a drop of water, just to show you what's the difference between explosion and splashing water, right? And we will first look from above, and then we will look actually through the water. And yeah, well, let's stop talking and let's watch a movie. Okay, so we have this drop, and it's falling, and it's just hitting water, and you see there's this explosion right on contact. And some of you may have noticed this blue flash. It's not the green flash from California, it's the blue flash, or purple flash. We'll get back to it. Keep going. It's really slow down. All right? Now we play it again, and this is sodium-potassium alloy, and this is a water droplet. So this is splashing, this is explosion. So I hope you believe me, explosion is a little bit more than just splashing water in water. So we play it once again, and then we will look through the water column now. So this is explosion, this is just splashing, and it was pretty fast, so we'll play it one more time. And watch here what's going on. I mean, we have this drop hitting, and there are these spikes, there are these metal spikes shooting into the water. So there's something happening. We had this beautiful metal ball, and when it hits water, it turns into, in Europe I would say hedgehog, here probably into a porcupine, right? And it's shooting the needles into the solution. So what makes this perfectly round metal to actually squirt metal spikes into the water? Well, yeah, there's few. This is just like, once more, we're dropping it on water. You see the spikes here. It's best seen from the bottom view right here. And the spikes are there for about 100 microseconds. So you really, yeah, this $200 camera wouldn't do justice to it. But with the high-speed camera, we could get it. And again, you see this blue flash here. We'll get back to it. By the way, it also works in liquid ammonia, but it's another story. So now we thought, okay, so we're not experimentalists, we're theoreticians, so we can actually model it. So this is a computer model of an explosion. It does not explode the computer, but you can model it on the computer. So this is a piece of sodium, which is surrounded by a piece of water. But just to give you a flavor, this is about 4,000 atoms of sodium. If I drop it on the floor, we wouldn't find it, even if the lights were on. It's so tiny. So it's a tiny, tiny model of the explosion. But this tiny model, we can actually follow each atom going. So this is what calculations can do these days. And if we do it, we can sort of replay what happened, what we saw in the camera. So you see this thing kind of expanding, and there are these little spikes going in. This is like a microscopic version of the explosion played on the computer. All right, so we can do it in real life, we can do it on computer, but do we actually understand what's going on? Well, actually we do. And as usual, when you invent something new in science, you realize that someone has done it already. And this time it was about 1880, so it's not that bad. So what's going on here? Why did we get... Are you sleeping all, or can you see me? Can we get a little bit of light? Just... because I may fall asleep otherwise. Oh, it's working on. Okay, cool. But you can sort of see me, right? Yeah, so what's going on here, right? So back to the teacher's explanation, what's going on. We have this piece of alkali metal, and the electrons are leaving into water, right? And it's true. I mean, what teacher says is always true, right? And we also know that the electrons are carrying a charge, right? What is the charge of an electron? I want to answer from people below 15. What is the charge of electron? I mean, yes. Negative, -1 electron charge. Perfect. So, oh, thanks, that's perfect. So electrons are carrying negative charge, right? And the piece of sodium was neutral in the beginning. And now many, many zillions of electrons moved into water. And that's what the teacher tells you. But no teacher ever told us that if many, many negatively charged electrons leave into water, what's left must charge positively, right? Because it was neutral in the beginning. So there's a huge positive charge on that alkali metal droplet. And two positive charges attract each other or repel each other? Plus, plus? Repel, right? Like charges repel, opposite charges attract. So if I will have many, many charges on this droplet, they will repel. And this thing is actually called Coulomb explosion. They even call it explosion. So this squirting, this porcupine/hedgehog effect is nothing more than this huge repulsion from these charges that are overcoming the integrity of the droplet. And this is, by the way, the mixing mechanism, the missing link in the mixing. But we've really rediscovered something that this guy, Lord Rayleigh, predicted in 1880s in a different context. He said if you take a water droplet and you charge it above a certain threshold, it will break into this thing, so this pattern where you get these spikes. I mean, we have many more charges, so we get more spikes, but it's pretty much the same pattern. And by the way, basic science meeting practical applications doesn't happen very often, but sometimes it does. You can use this to get big molecules like proteins into the gas phase by actually charging these droplets. It's called electrospray, and it's very useful if you do mass spectrometry. That's where we end. I may just say, I mean, it earned the guy's 2002 Nobel Prize, so it's not complete. It's important. Anyway, so we just, put new clothes on an old story and just published it. So now we understand why the chemical explosion can happen, because it's preceded by this electrostatic Coulombic explosion that mixes the water with the metal, and then boom, it can explode. All right. Now, the rest of my time, I want to talk about the blue flash. The green flash in California I've seen once, and it's a completely different thing, so it's a sidetrack. But anyway, okay, this is a question probably to more the Telluride people. So who has ever thrown a piece of sodium in liquid ammonia? All right, at least one. There should be more, right? So you can liquefy. Ammonia is a very stinky gas, but if you cool it to below minus 30 Celsius, which would be 0 Fahrenheit-ish, I'm always kind of ishy here, then it condenses and you get a liquid. And if you throw a piece of sodium into this liquid, it doesn't explode, but something beautiful happens. Monty, what happens?
It turns the most beautiful blue.
Yes, it's like this most beautiful blue ink, and then it gets black. Because these electrons are actually blue. Well, they are red, but because we have white light, they suck up the red. What we see is the residual, so it's blue. It looks beautifully blue. I mean, if you can convince your parents to buy a cylinder of ammonia and dry ice, you can do it at home, and it's pretty safe. I'll send you the sodium by email. Anyway, people have known it from 1803, and it was Humphrey Davy. So it's an old story. But in water, we don't see it because everything explodes, right? So if it all happens in 100 microseconds, maybe there was some blue, but nobody has seen it before. So this blue flash that you've seen, and you are among the first 1-2 million people who have seen it, is this actually the electrons? The electrons in water were discovered only in 1962. That's only 4 years before I was born, so this is historical time. And they had to invent techniques that are very fast. The electrons live in water shorter than a millisecond, so less than 1/1000th of a second. It's an eye blink, right? So, by the way, I mean, you know it from films, right? If something is faster than 25 frames per second, we don't see it. We see a continuous movement. So this is like 1,000 frames per second. We can't see them. Okay. Can we? Well, okay, so this was our new setup. So in the meanwhile, we moved to our core institute where they were renovating everything, and suddenly we lost the balcony, which was a disaster, right? Because we didn't have a place to do the experiments. So I actually convinced our director to give us a small lab. And then there was one caveat. He said, no more explosions. All right, so we totally redesigned the experiment. We did exactly the same as before, but except of dropping this drop from about 1 meter to water and exploding it, we very gently squirted it from like a needle and very gently put it on the surface of water. And that, starts the reaction, creates a bit of vapor, and the reaction runs, but it doesn't explode. And it's even more fun. Sometimes non-explosions are more fun than explosions, and let me convince you about it. And this you can actually shoot on an iPhone. So what happens is, look at this ball, right? It gets blue, black, then there's like a blue vapor coming out, then it gets like red hot, and then the miracle happens. A metallic droplet becomes like a glass marble. It lives for about a second or two, and then it pops, and it's over. I played one more time. So this is almost like real time. This whole thing takes about 3-4 seconds. It gets blue, black, then there's a blue vapor, then it's heating up. It's such a rich chemistry and such a stupid thing. easy, easy. But it's just beautiful, right? I mean, science can be beautiful. The more dumb it is, the more beautiful. Well, that's a hypothesis. Anyway, so let's analyze these phases one after another, right? So at the beginning, we start the reaction, but in a non-explosive way. And something starts happening, right? It turns blue. So are we actually seeing these blue electrons? I mean, not everything that's blue is electrons, right? I mean, your blue jeans, it's indigo. So not every blue color is electrons. How about this blue color here? How hot is it? I mean, it gets hot red, right? Can we estimate the temperature? And then, this is a miracle. This is alchemy, right? A metal, 2 seconds later, it looks like a glass marble. And then what happened with the glass marble? So, well, let's have a look. So, how do we find out it's electrons? We know how the spectrum of the electron looks like. It's kind of like a broad blob. It's boring, but it's cute. And so this is known, the black lines are known, and then we bought like $500 spectrometer and just recorded the spectrum of this blue thing. And it pretty much fits. So these are indeed electrons. So how comes we can see electrons that live only a microsecond when our eye needs about 50 microseconds to see anything? Well, the trick is, it's called steady state. And it's nothing else that we have this metal that is pumping the electrons into the water, and they react, but there is a short time where they're being pumped faster than they can react. So we have about 1 second window where we can see them, and it's really cool. I mean, and people were not sure we can see them with naked eye. I'm not sure what it is good for, but it's beautiful. Anyway, then there's this blue vapor, and that's when the droplet, because the reaction creates heat, it heats up, and it starts evaporating the metals. So this is another blue. And again, we can take the spectrum and we can see a signature of sodium and potassium of the two metals. And this shoulder here is the heat. It's the infrared. It's like your stove. You heat your stove red hot, right? And if your stove is red hot, you can actually, there's a formula, you can actually calculate the temperature and how much you will get burned if you put your hand on it. So doing this, we actually can estimate, this is about 600 Celsius, which in your units would be, well, help me, pretty hot, yeah. Yeah, I don't know. Can it? Really hot, like hot, yeah, okay. Like you would really burn. What's 600 Celsius in Fahrenheit? Thank you, about 1100 Fahrenheit. Take or leave, few Fahrenheits. Okay, and then the biggest beauty, right? This marble, what is it? What is it? Well, we know that the final product is hydroxide. I told you, that's the thing you clean toilets with, or your parents do, or I do. Yeah. So could it be hydroxide? But hydroxide, who's seen hydroxide? Can you buy it here in the drugstore? Yes, you can. So how does it look? Who bought it? I did. It's kind of like a white hygroscopic powder, right? And you don't want to really touch it with naked hand because it's lime. Anyway, so it doesn't look like this, right? But we said we have 1100 Fahrenheit, right? And it's not room temperature. You can actually melt it. It melts at about 400 Celsius, so 700 Fahrenheit. Don't take my word for it. So maybe it's a molten droplet of hydroxide. That looks like a cool explanation, right? From a metal droplet, we made it a molten droplet of hydroxide. And it's really cool until we realize there are two problems. One problem is that hydroxide is heavier than water, about twice as heavy as water. So it shouldn't be on the surface of it, it should sink. The other problem is it's perfectly miscible with water. If you throw 1 kilo of sodium hydroxide into your toilet, where it's 1 liter of water roughly, it will perfectly dissolve. And what we've seen is it was more like an oil droplet on water, right? So how come? Well, with the Coulomb explosion, we went to the 19th century. Now we have to go back to the 18th century. There was this guy called Johann Gottlieb Leidenfrost, and he noticed that if you throw water on a hot stove, you create these droplets. You may have seen it. Most of you have probably seen it, right? If you kind of accidentally spill something when you're cooking on a hot stove, it creates these droplets. And they're quite stable. They're stable because there's a little bit of water that evaporates, and it creates kind of a cushion on which this droplet can survive. And what we're having here is kind of an inverse Leidenfrost effect when we have a hot droplet on a cold stove on the water, and there's a bit of vapor that creates this stable thing for about 2 seconds, and then the droplet cools, and then it very fast melts into it. And by the way, we can prove it's hydroxide because we can take a spectrum of this droplet. This was a fantastic experimental improvement that we made. When we let this droplet roll around, we took a tea strainer and we picked it up. before it kind of exploded, and then took the spectrum, and lo and behold, there was a lot of hydroxide. All right, that's how theoreticians make experiments and then publish it. All right, and I'm coming to the end because I think I'm almost out of my time. One more minute. I want to tell you about future work because this is not finished. We're moving ahead. What we're planning to do, we're planning to pump a lot of electrons into water ideally, and then see how they behave. Because this is what Monty was referring to, this most beautiful blue color. But actually, if you're putting more electrons, it gets black, so that looks boring. But if you start adding more and more, it turns gold. And nobody has ever seen it in water, and we may never see it in water, but people have actually seen it in liquid ammonia. And we want to kind of revisit that and kind of study it intensely. For this, we're renting this machine, which is called a synchrotron. It's about the size of a soccer field. Yeah, you have to have friends there to let you in. And the way you do it is you make a liquid ammonia and make a tiny little jet, and you kind of squirt it into vacuum, and then you would like to add more of this sodium into it, and then study it and measure spectra. And these are the first spectra. And I'm just going to show you what you can do. But I want to end with a more artistic picture of what we'll try to do. So I'll show you a primitive setup that you can do even without the synchrotron. And that is, you take a droplet of a sodium potassium, and you put it on a cold finger. So you cool it to, say, minus 50 Celsius. So where are we? Minus 50 Fahrenheit? No, 40, something like that. And you blow ammonia on it. So your parents already bought you this cylinder of ammonia, so you just open it and blow it on it. And the ammonia will condense on your droplet. And this way, you go to these high concentrations, because now we are not dissolving the metal in ammonia, we're dissolving ammonia in the metal. So we immediately go to this high concentration. And the thing is golden. It's just beautiful. So it's so beautiful that we made kind of a Christmas movie out of it. So I'll play the Christmas movie to you as a kind of bye-bye thing. So this is the sodium-potassium alloy thing, and now we're blowing ammonia, and then we open it and close it, and you see this golden color? This is many, many electrons, not just like the blue color. This is golden color. And then you close it, and the metal actually starts kind of expanding, and it's like a Christmas, whatever, like glass, the top of a Christmas tree, if you wish. So enjoy, yeah. Zero science here, but it's beautiful. Anyway, I think on that note, I will finish my scientific talk, but I need to thank the people who did the work. So the biggest wizard is Phil Mason. He's here in this fiery shirt. A new postdoc, Tillman, who came from Germany, and 3 people doing calculations, Tomasz, Frank, and Andre. So I thank all them. I thank my collaborators, some bread givers, and of course I thank you very much for your attention.
Oh.